So today I want to talk about some important results that will be the preparation for the proof of the Kohn theorem and of the extremal contraction theorem. The first one is the so-called rationality lemma. So definition: X smooth surface over C, projective. Okay. Assume Kx is not an F. Okay. The F threshold okay, take an ample device of H. Okay, Th of H as Th is the sup of the T such that H plus Tkx is an F. This is actually a maximum. Okay, the important rationality lemma says that actually this is a positive rational number. So this is in R a priori, but actually is in this situation this is a positive rational number. Okay, what is the interpretation of this threshold? Okay, geometric remark. Before the proof, let me give a remark. Geometric interpretation. So we start, okay, Kx non-F. This means that the Mori cone, okay, intersects the half space and 1 x kx less than 0. Okay, there is a curve such that has negative intersection with the canonical class. Okay, at t equals 0, this hyperplane does not intersect and E. This is because of the Kleiman criterion. So we are in this situation. This is the hyperplane. Let me draw the cones as a section, So this is part of the Mori cone. Here there is something else, I don't know. This is a part of the cone where I draw this in this way because there is a reason. We will see the Kohn theorem. Let me draw this in this way. Locally polyhedral in any part here. Okay, anyway, so there is a part which is in Kx negative. Some part maybe in Kx positive. And then here is 0. Here we have this hyperplane, H orthogonal. H orthogonal does not intersect the cone because of Kleiman. Okay. So all the cone is in the with respect to this hyperplane. Here there is the part negative part. Here there is the positive part. all the cone is in the positive part with respect to h. This is Kleiman. Okay. When I move this, when I rotate this, there is a certain point when this ample, at a certain point, it touches the cone. When it touches the cone, here we have the Neff threshold. It is the first moment in which the divisor becomes Neff, but not ample. And then it enters the cone here. Okay? So here, let me draw here more. Okay. Here is h plus thk. And here we have h plus tk x t greater than th. And here we are the case where t is less than th. Okay? So th corresponds when h plus tk orthogonal rotates from its initial position at a certain point it cuts an e of x, and th is precisely the value where it first hits the cone. So here, in this case, h plus thkx is Neff, because the cone is still all on this part, but it touches here, so it's not ample because of Kleiman. And th is the minimum value for which h plus thkx is Neff but not ample. And the rationality lemma tells us that this happens at a rational number. It's not a real number, but it's actually a rational. It is a real number, but it's actually a rational number. Okay. So, sketch of this proof. This is important because now this guy here is a Q-divisor. Otherwise, but this is a Q-divisor, and this is important for the sequel. I have not, the time is limited, so I just can give a sketch of these proofs, but I hope to give the idea. You can find the proofs in the R book and in the other books that I gave to the organizer when they asked me for some literature on the topic. In Reed's book on algebraic surfaces, there is a proof as well, and so on. Notes, lecture notes. Okay, sketch of the proof. Th greater than 0, not difficult. Just use the fact that the linear functionals z to hz and z to kxz have non-zero maximum and minimum on this sphere. Okay, this is a compact subset. This intersection of the unit sphere with the Mori cone is a compact subset in a finite dimensional vector space, so it is a compact, bounded, enclosed in a finite dimensional vector space, so it is compact, and then this function will have maximum and minimum. They are non-zero, and then using this, it's not difficult to see that this number must be non-negative, strictly non-negative. Okay, once we do this, okay, now step 1. This is step 0. Step 1, we do this. Assume that exists M in N and T1 rational number such that this D1 MH plus T1 KX is effective but not nef. Okay, in particular, this implies that T1 is greater than TH. Okay, if then in this case, we have that this TH is the minimum over gamma in D1 of H gamma divided by minus Kx gamma, and this is a rational number. Why this? Okay, where gamma rounds over the irreducible components. Gamma, okay, of D1 such that Kx gamma is negative. In fact, why this? This is quite simple. Okay. In fact, just write this, for all t between 0 and T1, we have H plus TKX can be written as 1 minus T over T1 H plus T over T1 times 1 over n D1. Okay, and this is a positive and rational combination. Combination of H and D1. We are assuming that this is effective. This is ample. So the only possibility for H plus TKX over gamma less than 0, so the only possibility for this divisor not to be nef is that there is a curve here that intersects this negatively. But this divisor is a combination of an ample positive and rational combination of an ample divisor and an effective divisor. So H times this is always positive, strictly positive, Nakaimo-Ishizon. So the only possibility is that gamma intersect negatively this one. So in other words, this means that gamma is a component of the one. So the only possibility for this is that gamma is a component of the one. It must be a component which intersect the canonical class negatively, otherwise, such that okay, x gamma is less than 0. Okay, and so this is step 1. Step 2. Step 2, we try to reduce ourselves from the general situation to step 1. Okay, choose m n positive integers such that we have m th between n and n plus 1. You can do this, namely n over m th n over m plus 1 over m. This is a positive real number. In step 0, I proved it is positive, so a positive real number. I can find two fractions such that we have this. Okay, then, by definition, I have that mh plus nkx is ample, because it is before, this is clearly, but we have that perfect mh plus n plus 1 kx is not m, is not even f. If you see the picture, if you look at that picture, in this case, the yellow hyperplane moves, but it does not touch the cone yet. So we are still in the ample case. In that case, we moved after the F threshold. We hit the cone. We're inside the cone, actually. So in this case, it's not even F. Okay? We passed the F threshold. This is strictly before the F threshold. This is strictly after the F threshold. So ample here, not even F here. Okay? Well, the ampleness of mh plus nkx give us, using Kodaira-Vanishing theorem, the following thing. We have that hi of x mh plus n plus 1 kx. We can write this as hi of x m kx plus mh plus n kx. This is ample. Hi of something canonical class plus something ample is 0 if I is strictly greater than 0. This is Kodaira vanishing. We are in a surface, so 1 and 2, it's okay. Then the growth of H0 is given exactly by Riemann-Roch because we have no Eiger cohomology. Then by Riemann-Roch, we have that H0 of x mh plus m plus 1 kx. This is equal in this case to chi. Because there is no H1, there is no H2. And this is, in this case, do the computation, is mh plus n plus 1 kx mh plus n kx divided by 2 plus k of ox. Okay. And this is equal, I will explain now, 1/2 m squared d0 squared plus m 1 minus 2 alpha d0 kx minus alpha. Okay, 1 minus alpha k x squared, perfect, plus chi, where we set mth is n plus alpha, and alpha is between 0 and 1, and d0 is h plus th kx, so d0 is an f, but not ample. Okay, so we are in this situation. The growth of this can be written in this way, where alpha is between 0 and 1, because remember that we choose mth between n and n plus 1, so there is an alpha such that does this, and it's exactly this. Okay, now there are 3 cases. It depends on the growth of the, it depends on the behavior of d0 squared. Case 1, subcase. This is 1, A, d0 squared is positive. Okay, so in this case, this h0 of x mh plus n plus 1 kx grows quadratically with m as m squared, because this is positive. This is an f, so d0 squared cannot be negative. Okay, perfect. Then for m big enough, we have that 0 is strictly big, or if you prefer, h0 of x m h plus n over m plus 1 over m kx. This is strictly bigger than 0. Okay, now set T1 equal n over m plus 1 over m, which is bigger than Th. So we are in case 1. We are exactly in the situation described in step 1. This is effective but not nef. So we are in the situation described in step 1, and we conclude. So we know that this is not nef. Where is nef? Okay, I said it here and there. This is not nef, but it's effective. So we are exactly in the situation described in step 1, and we can conclude that in this case, the nef threshold is a rational number. Now, we must analyze the remaining case where d0 squared is 0. So, subcase B, d0 squared is 0. And there are two possibilities. Either it is not numerically trivial or it is numerically trivial. Assume that first this is not numerically trivial. Not numerically trivial. What we can say in this case? Well, in this case, dH, okay, d0h is greater than 0. In fact, d0h must be at least 0 since d0 is nef and h is ample. And so a multiple of h is effective. And so this is, since this is nef, must intersect non-negatively every effective class. Now I have to show that d0h equal to 0 is impossible. This is a consequence of Hodge index theorem. No. T2 and T1 down. Where is here? On the other hand, if d0h equal to 0, then d0 squared must be negative by Hodge index theorem. Recall that Hodge index theorem says that the intersection form in the num has just one positive eigenvalue and all the other are negative. So h, you can take as h as, the divisor corresponding with the element of the base corresponding to the positive eigenvalues. So this is in the orthogonal. Since it is in the orthogonal, either it's 0, this means numerically trivial because we are in num, or it must be in the orthogonal, so it must have negative self-intersection because of the intersection form as signature 1, rho minus 1. So if this is 0, the only in this case we are assuming that the 0 is not numerically trivial, so necessarily it should be of negative self-intersection by Hodge index theorem. But on the other hand, we are assuming that the 0 square is 0. So this is not possible. By Hodge index theorem, impossible, because the 0 square is 0 by assumption. So the 0h, yes, greater than 0 as claimed. Therefore, we have the following thing, that 0 equal the 0 squared, and this is the 0 h plus th kx, and this can be written as d0h plus th d0kx. This is strictly positive, and so this implies that this is strictly negative. Then, look at the asymptotic expansion given by Riemann-Roch. Where is it? Yeah, it's upstairs. We have 1/2 m squared d 0 squared, d 0 is 0, so there is no d 0. M minus 2 alpha d 0 kx. D 0 kx is negative. And 1 minus 2 alpha is negative as well, because alpha is between 0 and 1. So there is a positive coefficient in front of m. And again, we have in the situation of step 1. Then, choosing m greater than 0 and arranging this can be done in such a way that 1 minus 2 alpha is strictly negative, we obtain H0 of x mh plus n plus 1 kx. It goes as is written there, m 1 minus 2 alpha, and then there is d0 kx. And this goes as a constant, positive constant times m, positive. And so this is greater than 0 for m big enough. Again, by step 1, we are done. Yeah.
When you say arranging in such a way that this holds, there you use approximation business.
Yeah, there is some approximation, some Diophantine approximation business. I have no time to tell you. So arranging n means that do some little approximation by continued fraction, for instance. Yeah, you're right. But the time is not so much. Small argument involving rational approximation. Continued fraction, for instance. You can do it. In Ciliberto's note, I suggested there is the complete argument. But anyway, it can be done. OK. And now there is the last case, the easiest one, when d0 is numerically trivial. This is completely simple. Case 3. We have d0 numerically equivalent to 0. In this case, given any effective curve gamma inside X, we have that 0 is equal to T0 gamma, and then, in this case, this is H plus THKX times gamma. And, OK, so TH is just H gamma divided by minus KX gamma, and this is rational. And we have completed the proof. Yes, the proof is, whenever you look at the textbook in which this proof is given, more or less the line of the demonstration is this one. I mean, some small argument can change, but the core of the proof is essentially this. So it's a little bit involved, but actually it's not very difficult. It's just some kind of playing with divisors and their properties, and do, at a certain point, some little rational approximation here. But it's not difficult. Well, so the geometric interpretation we have done, and now there is another big result, which is base point free theorem. Sorry. Yeah.
Does the same argument work in higher dimensions?
it's more complicated. It is still true, but it's more complicated. You can look at, I mean, of course, here we are using a lot of stuff for surfaces, for the Hodge index theorem and so on. But you can do it in higher dimension. There is actually, at least for threefold, there is the proof in Collar-Mori. I'm sure that there is the proof of rational threshold. I think that in Collar-Mori you can find the proof for threefold, but it's more involved. It's not exactly the same argument, because here, of course, we are using also a lot of stuff about surfaces. For instance, this formulation of Hodge index theory, and moreover, we are assuming that everything is smooth. Wherever, for a minimal model program in higher dimensions, it is necessary to have a version of this which works at least for some kind of controlled singularities. So it is more involved. You can find the statement in Collar-Mori book. So regarding also for the next theorem, which is Beit Poetry Theorem, which is quite complicated in higher dimensions, but for surfaces we can give a proof. So at least a sketch of a proof. Theorem. Base point 3. So X smooth, complex, projective surface. H ample. Let T in Q positive rational number, and consider the Q divisor D equal H plus T kx T. Okay, we already saw this. And assume that D is an F. i.e., this means that T is at most the F threshold. Then the linear system given by complete linear system MD is base point 3 for all sufficiently big and divisible M, okay, sufficiently big, so such that MD, yes, of course, this must, not MD. This must, in order to talk about linear system, it must be an integer divisor, so MT is natural. So this is the statement given in Matsuki, for instance, or also in these notes by Ciliberto, which are inspired to Matsuki as well. So the statement is one. You have an ample divisor.
What do you mean with divisible? Divisible.
Divisible means that at a certain point you must clear some denominator, some finite number of denominators. And so you require some property of divisibility, but apart from this, it's big enough. But you must clear some denominator at a certain point. So you need that this number is big and is divisible by a finite number of integers. This is a technical problem because I think that there are versions, more complicated versions in which this property, this requirement is not, this is not required. But for this proof, it is a technical, is needed for the technical way in which I prove this statement. But, okay, so if you have an ample divisor, you consider this number, this divisor, h plus kx, and if this is nef, then it is eventually base point free. For m very big and with additional property of sufficiently divisible, it is base point free. Okay, proof, sketch, very sketch, very sketch, proof. Okay, dnf implies d square non-negative, so we have three cases. Case 1, d square greater than 0. Okay, so if d is ample, nothing to prove. If D is not ample, then there is, so this D square is greater than 0, okay? So recall that by Nakaimo-Ishizon, if D intersects every curve positively, it must be ample. So we are assuming that it is not ample, so there is a curve which intersected with it is 0 because it's nef. Then there exists an irreducible curve E in X such that 0 is equal D times E, and this is HE plus T kx E, and this is greater, this is positive because H is ample, and this is greater than T kx E. So kx is negative. Very good. Okay. Moreover, by Hodge, okay, this is a divisor with positive self-intersection. You can take a base of num such that this corresponds to the positive eigenvalue, and then all divisors intersecting, all divisors in the all divisors in the kernel of the linear function d times x must be clearly either numerically 0 or with negative self-intersection. This is Hodge index theory. In this case, this is not numerically trivial, of course, because it's an effective curve. So we have E squared negative. Because it is in the kernel of something which has positive self-intersection. In the kernel, I mean it is in the D orthogonal, and D is positive, so it's big. And so by Hodge index theorem, it must have negative self-intersection. And so we are done now. This is a -1 curve. So we have kx E plus E squared divided by 2 plus 1. This must be 0 is greater than or equal to this. This is the genus, arithmetic genus. And these are both negative. So the only possibility is that this equal -1. This means that E is isomorphic to P1, and E squared is equal -1, and so this E can be contracted. this is the exceptional divisor of a blow-up. By Castelnuovo theorem on surfaces, every curve with these properties is the exceptional curve of a blow-up, so it can be rationally contracted. This is Castelnuovo theorem. Okay, so we have a contraction map. Can be contracted to a smooth surface. Okay, so there is a contraction morphism P from X to X prime E to P smooth point. So this is, okay. Well, okay, and we see that, yes, and now setting very simple computation, H prime and yes, we see that H prime is ample on X prime. Very good. And that we have that P lower star as a cycle of D is just given by H prime plus P K X prime, because the exceptional curve is contracted, so we have this.
How we can say that there are no more exceptional curves? We should do this.
No, this is just the contraction of E. We can be other, yes, but at a certain point they finish because the Picard number drop by 1 every time. We can repeat this to H prime, to X prime now, okay? Okay. If D is ample, okay, so, okay, very good. Let me call this D prime. I'm sketching the proof. You must check something, but this is very simple anyway. Okay, if D prime is ample, this is eventually base point free, and so from this it's easy to see that also this is eventually base point free. Base point free, and so is D. I mean, this is very simple because the fact that here we have this fact is simple because Kx is P upper star of Ax prime plus E. When I apply P lower star, E disappears because it's contracted to a point. So we have by projection formula P upper star, P lower star is just the identity. So not difficult. This is a pullback of cycles, not a line bundle, of course, the pullback of cycles. Yeah, the push forward of cycles, sorry. Okay, so if D prime is not ample, by the same argument as before, there is a -1 curve here. there is a -1 curve E prime in X prime. We can contract it and repeat the reasoning. And on. Repeat the argument. By the way, d square is so we are exactly in the same situation as before. Exactly in the same situation as before. We can contract it and repeat the argument. The process stops after finitely many steps because at each step the picker number drops by 1. So the case is done. The picker number cannot become 0 because we are in the projective situation. So at most after rho of x steps, rho of x minus 1 steps, we are done. And now here, case 2. This is the okay, I wrote case 2. D square 0 and d different from 0. Okay. First of all, we have the h greater than 0. In fact, the h is at least 0 as before. And if the h equals 0, by Hodge, we should have the square negative contradiction. So this is not possible. Okay. Then, now, we have 0 is equal to d square, and this is d, sorry, h plus t kx, and this is dh plus t dkx. So this is bigger than t dkx, and from this we have that kxd is negative. Okay, and so we must work a little bit. I think I have no time to work out all the details. Yes, okay, working a little bit now. We found what follows, that for m sufficiently big, we can write md in this case as fixed part plus a movable part. So this is a movable part. And this is nef. And this the rest, the fixed component, fixed part. And 0 is like this. By nefness, again, we have this because everything is effective. And this is m, md. This is again in this way. And this is m squared, d squared. This is 0. So m squared equal mf equal 0. And so f squared equals 0. From this, it follows that from this thing, it follows that this is composed with a pencil. And f squared equals 0, this means that and fm equals 0 means that the fixed part is contained in fibers of the pencil. Because it does not intersect the pencil. Okay, but now then, Stein factorization plus Zariski's lemma does the job. Okay, the point is that by Stein factorization we have a real fibration, I mean connected vibration, and so this M moves, but there is the problem of the fixed part. But the fixed part is contained in fibers. But f squared equals 0, so by Zariski this must be a rational multiple of a wall fiber, a rational multiple of a wall fiber, sum of rational multiple of wall fibers. And so if we take M sufficiently divisible, I can eliminate all denominators, and so this is really now then something that moves. Okay. So, taking M and sufficiently divisible, M, F moves, and so without base points, and so does MD. Okay, and I have 3 minutes just to finish the last case. Thank you very much. Remark? In this case, at the end of the day, in this case, there exists a map from X to C. C is smooth curve, and general fiber isomorphic to P1. Just take the Stein factorization of this stuff, and in this case, we have this. Because Kxf is negative, and I mean, you can do this. Okay, just 1 minute for the last case. I will erase here. So in the first case, d squared greater than 0, there are contraction of -1 curves. In this case, there is a fibration, a smooth fibration with general fiber P1. And then there is the third case. And the third case actually is P2, case 3, but I cannot prove this. D numerically equivalent to 0 in this case. For all M, we have MD plus Kx. This is 1 over TH, which is ample. Okay, so Kodaira. We have that hi of x md. This is hi of x kx plus md minus kx. This is 0, E1 and 2. For m equals 0, this gives h2 xox is equal h1 xox is 0. And so chi xox is 1. And for general m, we have that h0 of x md is chi of x md, and this is md minus chi divided by 2 plus chi of x. This is 1, this is 0, because d is numerically trivial, so this is 0. This is 1, so this is 1. So md is effective. Since md is also numerically trivial, the only possibility is that d is trivial, and so is base point free by definition. Okay, so we proved we gave a sketch of the proof of the base point free theorem. And I think, sorry for 3 minutes of overtime, I think I can stop here. Thank you.